Okay, this separate video is going to cover the second half of the Chapter 6 notes. I think it's kind of a little bit too big to try to take in one chunk. So this will cover the second half of the Chapter 6 notes. So I'm picking up on the next slide of the printed notes if you're using them for Chapter 6. This is going to be determining when it's appropriate to say that something is a normal distribution. Sometimes we can just look at the histogram and it looks approximately normal and we're good. But there's another way to do that as well, okay? In earlier chapters, we said that we should really only use the mean and standard deviation if a distribution is unimodal and symmetrical. And sometimes that's referred to as the nearly normal condition. So the thing is close enough to a normal curve that we can use normal tactics to analyze it. And there's basically two ways to determine if a data set is nearly normal. One of them is to look at a histogram of the data set and just see that it's approximately normally shaped, now that we know what a normal curve looks like. And the other one is to construct something called a normal probability plot, which is abbreviated NPP. It's also known as a quantile plot. So we'll look at that, okay? If you have data, and let's see, do I have an example that we can look at? Yeah, if you have data, I'm going to show you what you can use. Let's actually look at a set of data, and I'll show you. So I'm going to switch to the view where we can see the calculator, because this would be calculator oriented, so you can follow along with this if you have your calculator with you. Okay, so let's just make up a set of data. We're going to go ahead and turn on our calculator. Let's clear our lists. So I'm going to do that by going second and then the plus key to get to the memory menu and selecting number 4, clear all lists at once. Then I'm going to go stat and then hit edit to go into the lists. And I'm going to use list 1. And let's just make up some data. So how about this? Let's go 8, 12, 15, 16, 18, 19, 20, 20, 22, 24, 25, and 31. Okay, it's totally made up on the spot. And the first way we would try to determine if this data is approximately normal would be, well, let's take a look at the histogram. So the way we could do that is go second y equals, turn on statistics plot 1, make it a histogram, make it, that's this icon, make it list 1, make sure the frequency is set to 1. If that still has like list 2 in it, you can hit delete and then enter and then manually put 1 back in there. And then we can display it by selecting zoom 9, which is statistics. Okay, so this right here, yeah, I would say that's probably nearly normal, pretty close. One thing that bothers me a little bit, it's not so much that this on the left is a little too high, it's more that there's a gap here. Right? The reason why this is this way is we put such a small set of data in. It's like there's not even really enough. This could be normal data, and we just don't have enough to fill it in, so we get a nice shape here. So that's where this other tool comes in. If you have a histogram that you're not really sure you can declare looks roughly normally shaped, like this one, you can run this thing called a normal probability plot. So here's how you do it. You go back to the statistics setup menu, second y equals, go into statistics setup menu 1, but you select the last icon, the one that looks like a line after the box plots, okay? And then it'll say data list, list 1, and data axes. You can leave all the rest of that stuff the same. Doesn't matter what you put here, so just use the default values. Say second mode to quit, and then zoom 9 again, okay? And that gives us a plot that looks something like this. Okay, so let me explain what this plot is. This plot shows the z-scores of a perfect normal distribution on the x-axis, and then it shows the z-scores of the actual data samples we have. And the idea is that if everything is kind of spaced out where it should be, then everything should be along a line with a slope of 1, because any data value should be about where it should be in terms of standard deviations above or below the mean, as it would be if it was in a normal distribution. And so this plot here, if it's roughly linear, and this is certainly roughly linear, then that means we can declare that this data is approximately normal, even though we have such a small set of data that we don't really have enough to see the mound shape very well. Right? So that's what this normal probability plot or quantile plot is used for. And let me show you the steps again. Second y equals, and you select the last icon. If you select the last icon and then display that, as long as you see something that's roughly linear, I see a little curvature here, but that's not a big deal. That's fine. Then that's evidence that you can use. And actually, in an explanation, if you needed to say the normal probability plot was linear, you would actually on your paper sketch this little graph and just show that what came out and use that as evidence for justifying the fact that you think it's a normal distribution. All right, so interpreting them, right? If you have a perfect distribution or pretty close, you'll have something that's pretty much like a line, okay? If you happen to have data that's skewed right, then the normal probability plot will have a curve in it like that. If it's skewed left, it'll happen to be curved the other way. And if it's pretty much flat and uniform, then this will have a really distinct S shape to it, right? So these all deviate from a line pretty substantially, right? And this thing that we did, that looking on my calculator here, this has a little bit of a uniform kind of deviation, but not enough to say that it's not normal, right? Only if something's really pronounced like this do we say that the normal probability plot fails to show that the data is normal. All right. Okay, the next topic we're going to talk about something completely different, and that is, what if we had a set of data? Like, let's say we had a set of data for how many credit hours, how many credits somebody took, right? And we have a distribution for a bunch of students, how many credits they're signing up for in college. And then we want to convert that data into the amount of money that they have to spend, right? That's going to give us a different distribution, which is the amount of money that they spend, right? And so there'll be some sort of a formula that we use to convert from one set of data to what we call a transformed set of data. We're transforming the data by doing something to it. Well, it turns out that depending on what we do, different things happen to the distribution. And the first thing is, if we just add a constant to every data value, if we just, like the transformation is just take the original data and add 10 to it to get the new data, then what happens is, actually in this case, what we did was we added 30, okay? So if I took data here, like this black distribution, which has, say, a point here that's 10 and a point here that's 50, and I just add 30 to everything, then everything just shifts up 30. So this shifts over to 40, this 50 shifts over to 80, and definitely what you can see is that the mean is different, right? Measures of center, like mean and median, are definitely affected, but measures of spread will not change, right? Measures of spread, like the standard deviation or the IQR, will not change, right? So adding or subtracting has no effect on standard deviation and IQR, although it does affect measures of center or any individual measure. On the other hand, if you did something where you multiplied by 2, so let's say that I multiplied everything by 2, I doubled everything in this distribution to get this distribution, like this 10 doubles to 20 and this 50 doubles to 100, then you can see not only does the mean change, right, but also the standard deviation, which is a different color, the standard deviation is getting wider, right? So everything changes when we multiply, okay? And that's important because we want to be cognizant of that when we process changes of data. And we're going to do an example here in a second to show what that's like. Okay, this is really complicated. And this, if you look at like the formula sheets for AP statistics, they'll say things like this on it. That says, if a new data set Y is found by taking an old data set and multiplying by A and adding B, then the new mean and the new median will exactly follow that algebra. We'll multiply by A and add mean, but the variance, the standard deviation, and the IQR will only be affected by the multiplication. The adding will have no effect, okay? So really complicated way to say that multiply affects everything, adding and subtracting only affects individual data values and centers, but leaves spreads like IQR and standard deviation unchanged. Okay, so at this point, normally I ask people to do the required practice packet problem 11, 12, and 13. Okay, so I would like you to pause the video and actually do that. Actually, you know what? Yeah, please do that, and then check your answers. Would that be good? Yeah, no, you know what? Let's do a different one. Okay, so yes, I would like you to do that. Do chapter 6 required practice packet 11, 12, 13, but this would be a good time for me to explain something using our practice quiz. So I'm going to pull up the required practice packet here. for 6, if I can. And we will go ahead and work some of the practice packet or the practice quiz at the very back. So you can do this with me by going to the back of the required practice packet for chapter 6. And we're going to look at the first part of the practice quiz. Okay, this is a really good problem that illustrates what we just covered in the notes. Okay, let's say that students take an intro to stats class and they report the number of credit hours that they were taking that semester. And the summary statistics are given in the table. Okay, so what that means is that we have a distribution here for the number of credits, that somebody takes, right? And it has some sort of distribution. I'm just going to draw it as a generic distribution. And we know that things like the mean is 16.65 credits, and the standard deviation is 2.96 credits, okay? And there's other stuff there as well, okay? Then we're going to transform this data because it says, suppose the college charges $73 per credit hour plus a flat fee of $35 per quarter. So for example, if a student takes 12 credit hours, they would have to take that 12 and they would have to multiply it by $73 for each credit hour, but then they add on the 35. So we're transforming this data by multiplying everything by 73 to convert it to dollars, and then we also have to add on the $35 fee. And then that will result in a new distribution, which is the amount of money that it takes to pay for the classes, okay? So what we're asking here is questions about the mean, standard deviation, median, and IQR for this new distribution. So how would we do that? Okay, so if you think about it, I'd like to think of it this way. The algebra for this is that the new value, I'm going to call this y, is related to the old value by this. We take the old value x, we multiply by 73, and then we add on the 35. So this is the algebra that represents this transformation of one data set into another. All right, so the mean is an individual number. That's a measure of center, and that means that it's going to be affected by both the multiply part as well as the shifting part, the plus 35. So that means that the new mean, which is the mean of the dollars, maybe I should just say it that way. I should just say it's the mean of the dollars, right, is going to be 73 times the mean of the credit hour, the number of credits, plus 35. So it will just be 73 times the mean of credits, which was 16.65, plus the 35, right? And that turns out to be equal to $1,250.45. So the average student pays $1,250.45 for their classes because on average they take 16.65 classes at $73 each, plus they pay a $35 fee. And both the multiply and the add affect the transformation. Okay, but when we look at the standard deviation, so the standard deviation for the dollars, right, because that is a measure of spread, that's going to be affected by the multiply, but it's not going to be affected by this plus 35, right? We said shifting does not affect any measure of spread. So we're just going to say it's 73 times the standard deviation of the credits, number of credits, but we're not going to add the 35. So it's going to be 73 times the standard deviation of 2.96. And that would turn out to be, again, same units, dollars, $216.08. So the standard deviation here is only 216.08, not that plus 35. And for the median is also a measure of center, so it will be affected by everything. So the median of the dollars will be equal to 73 times the median of the credits, which is 16, plus the 35. So we should get a median cost of $1,203.00. And then the IQR is a measure of spread. So first of all, we have to figure out the IQR for the credits. That would be 19 minus 15, which is 4. So since this is a measure of spread, only the multiplier 73 is going to affect this. We're not going to do the plus 35. So 73 times 4 is $292. Okay, so measures of center are affected by the multiply and the add, but measures of spread, like standard deviation and IQR, are only affected by the multiply part. Okay, so I just thought we should go over that before we go back to the notes, because that's a really good illustration of what we're doing here. All right, let's actually go back to the notes then and finish this off. There's one last problem we want to do, and this one's pretty challenging. It involves actually doing a system of equations too, which I will review. It says, okay, while only 5% of babies have learned to walk by the age of 10 months, 75% are walking by the age of 13 months. Okay, if the age at which babies develop the ability to walk can be described by a normal model, find the mean and standard deviation of the age at which babies walk. Okay, all right, so here's the idea. First of all, I'm going to look at what I have been given here, and I've been given some information. If I look at the data, okay, so I'm going to look at the data here. I know that they told me that it's normally distributed, but I don't know the mean, and I don't know the standard deviation. Okay, I do know though that 5% of babies, so 5% of babies down here walk by 10 months of age. Okay, this is the age at which they walk. Okay, I also know that over here that with that same mean and standard deviation for age of walking, that 75% of babies, so maybe about here, 75% of the babies are walking by 13 months. Okay, so that's all in the data distribution on a normal data distribution like that. But the problem is I don't know the mean and the standard deviation. So I can't really, that's what I'm being asked to find out. The problem is asking me to compute what are these values, okay? So whenever you're missing a mean or standard deviation, right, you can't really use the inverse norm inverse norm and normal CDF. So instead, we just punt and we go to using the z-scores. Okay, so I could write another distribution with the same information, except use z-scores. Now, z-scores, we always know the mean and standard deviation because it's 0 and 1. And if I put a line at that same boundary, right, where this is 5% of the data, I could use inverse norm to figure out what that value is. And I could also use inverse norm over here to figure out what this other value is. So for z-scores, I know this is 0 and 1. And there's a boundary here where 75% of the data, the babies are there, and there's some boundary here. So what I'm going to do is over here, I'm going to use inverse norm. So if I wrote inverse norm, the area to the left is 5% with 0 and 1 as I'm going to abbreviate this left area, mean, and standard deviation. I'm going to use a calculator. Okay, so if I did second variables inverse norm, and I put in 0.05 with 0 and 1, that's telling me that this place has a z-score of negative 1.645. So I have to be 1.645 standard deviations below the mean on a normal distribution to be in the bottom 5%. And so that's where this value is connected to, okay? And what I've just done is said that this z-score right here is connected to this data value right here, this data value x, okay? I'm going to do the same thing over here, so just bear with me until I finish this, right? If we said inverse norm with the area to the left of 75% and 0 and 1, left area, mean, standard deviation, I could use a calculator to figure out that in a normal distribution, 75% of the areas to the left of something that is 0.6745 standard deviations above the mean. So this z-score is connected with this data value of 13. And then what I'm going to do is use my z-score formula, which is z is the data value minus the mean over the standard deviation, to make an equation that connects these two. Okay, so filling in this x and this z into this equation gives me negative 1.645 equals 10 minus my unknown mean over my standard deviation. And doing the same thing to connect this x and this z is going to give me 0.6745 equals 13 minus the unknown mean over the unknown standard deviation. Then I'm going to do a little bit of manipulation here. I'm going to multiply both sides of these equations by sigma to get negative 1.645 sigma equals 10 minus mu. And then I'm just going to move the mu to the other side. So it's going to be mu minus 1.645 sigma equals 10. And I'll do the same thing over here. Multiply both sides by sigma. And then move the mu to the other side. Mu plus 0.6745 sigma equals 13. Okay, so I have two equations here, equation 1 and equation 2, and I have two unknowns. So it would almost be like a system if I had like this is x and this is y and this is x and this is y, and I need to find the one xy pair that makes those true. So I'm going to take those two equations and just move them to another screen real quick. Okay, I need to solve these two equations at the same time. Let me write them as if they were a system. Okay, so I have one equation is mu minus 1.645 sigma equals 10, and the other one is mu plus 0.6745 sigma equals 13. That's a system. If this was written this way, x minus 1.645 y equals 10, and x plus 0.6745 y equals 13, that might look a little more familiar. Like it's basically, this is algebra 1. Remember how we were able to solve this with elimination or substitution? Well, what we're going to do is we're going to use the calculator's RREF feature to do this. So I'm going to build what's called an augmented matrix, okay? And that's going to mean I'm going to take the coefficients. There's a 1 here and a 1 here, and then a negative 1.645 and a positive 0.6745 here. And I'll just put the right-hand side over here. This is a 2 by 3 matrix, right? So everyone at this point should have learned at some point, probably in Algebra 2 or pre-calculus, how to do this. If not, send me an email and I'll give you some videos to show you more about this, but I'm going to go ahead and show you the steps now. If you have a TI 83 or 84, you can go second and then matrix, the fourth key down, go over here and edit matrix A, set it to be a 2 by 3 matrix, and then enter these coefficients. So 1, negative, using the negative key, 1.645, and then, oops, I made a mistake there, so let me get back in. You can always just start over if you have to. Okay, 1, negative 1.645. Okay, and then hit enter. Nope, I got the wrong place here. 1, enter, and then negative 1.645. Trying to go too fast here. And then 10. And then 1, and positive 0.6745. 0.6745, and then 13. Okay, and once the matrix is in there, then what you do is you quit to the command line, go back to the matrix menu, second and the fourth button down, slide over here to math, and then scroll down to RREF, which stands for reduced row echelon form. Tell it, go back to the matrix menu and tell it to operate on matrix A. And then this will produce this matrix. So what I would say is I would show this matrix if I was doing this on a test. Say I did RREF, then I got this matrix, 1, 0, 0, 1, 12.1276, 1.2934 approximately. And since this column is the mu column and this column is the sigma column, this equation now says 1 mu plus no sigmas is 12.1276, and no mu's plus 1 sigma is 1.2934. So what we just found is, in our baby's distribution, we didn't know what this mean and standard deviation was, but now we know that babies on average walk at 12.1267 months with a standard deviation of 1.2934 months. So I should put the units on there. And then we're done. This problem asked me to find the mean and standard deviation of the distribution, but I had to use a lot of stuff here, right? Just to summarize, we wrote out the data distributions with the boundaries we were given, but our unknown mean and standard deviation. Since something was unknown here, we wrote corresponding z-score distributions where we know this is 0 and 1, and then we used the area to find the corresponding z-scores. Then we matched each z-score up with its data value using the z-score formula here to form an equation. And we kind of laid it out so it was in the form of x plus something, y equals a number. And then we treated that as a system and used a matrix RREF to solve for x and y, which was the mean and standard deviation. All right, so that concludes the lesson part for chapter 6.